Good morning. Our title is Design and Simulation of a Non-Isolated P-type Switched Inductor Boost Converter. The main aim of the project is to design a switched inductor boost converter to obtain a high voltage gain at a lower duty ratio. To design this converter, the boost converter has some significant drawbacks such as high voltage stress on switches and low efficiency. The analysis of the proposed converter can be carried out using MATLAB or Simulink. We have studied some papers to design this topology. The details of the papers are shown here. While coming to the problem statement, a boost converter can achieve a high voltage gain at a duty ratio nearly equals to the 0.9. There are some drawbacks while using boost converter. Output voltage will appear across the switch, so the voltage stress across the switch is more. There is a need of DC-DC converter design that can achieve high voltage gain with minimal switch stress, reduced power losses, and improved efficiency. While coming to the objectives, to develop a high voltage gain transformer-less DC-DC boost converter operating at a lower duty ratio. To design optimized circuit elements such as inductors and capacitors for the proposed boost converter. To reduce voltage stress on the switch and the other components, improving reliability. And this is the block diagram of our converter. While coming to the topology implementation, figure 2 is the boost converter and figure 3 is the P-type based boost converter, which is given in the studied paper. Figure 4 is the switched inductor topology. And figure 5 represents that P-type switched inductor DC-DC boost converter, which came by combining figures 3 and 4. And this is the final topology, that is P-type switched inductor boost converter. These are the on condition equations and these are the off condition equations of our converter. By using volt-second balance, we got the gain as 2 by 1 minus d for this converter. While coming to the stability analysis, this is the stability analysis for on condition and off condition. We have done small space analysis by using the above equations. These are the design parameters. We have taken the input voltage as 24 volts and output power is 100 watts, output voltage as 96 volts and duty ratio is 0.5 and switching frequency is 20 kilohertz. We got the output resistance as 92.16 ohms and output current as 1.0416 and input current as 4.166. Both values of inductors are same. So L1 is equal to L2 is equal to 1.4 into 10 to the power of minus 3. And we have two capacitances, that is capacitance C1 is equal to 289.3 into 10 to the power of minus 6 farad and C2 is equal to 27.1 into 10 to the power of minus 6 farad. This is the open loop simulation. These are the results of the simulation where these are the voltage waveforms. The first waveform is input voltage and second is output voltage and third waveform represents voltage across capacitor 1 and Fourth waveform represents the voltage across capacitor 2. These waveforms represent the current waveforms. The first waveform is the duty cycle, and second waveform represents the current through inductor 1, and third waveform represents the current through inductor 2. These waveforms represents diode voltage waveforms. First waveform represents duty cycle. Second waveform represents voltage across the diode 1. Next waveform represents the voltage across the diode 2. Next waveform represents the voltage across diode 3. Next waveform represents the voltage across diode 4. And last but not least, last waveform represents the voltage across the diode 5. This is the closed loop simulation. These are the results of the simulation, where these are the voltage waveforms. The first waveform represents the input voltage, second represents the output voltage, and next waveform represents the voltage across capacitor 1, and next waveform represents the voltage across the capacitor 2. These are the waveforms of current. First waveform represents the duty cycle. Next waveform represents the current through inductor 1, and next waveform represents the current through the inductor 2. These are the diode voltage waveforms. First waveform represents the duty cycle. Next waveform represents the voltage across the diode 1. Next waveform represents the voltage across diode 2. Next waveform represents the voltage across the diode 3. Next waveform represents the voltage across the diode 4. And last waveform represents the voltage across the diode 5. These are the specifications of our converter. Up to now, we have work done so far. Circuit design, voltage gain derivation, simulation, and waveform analysis. We are ahead to transfer function derivation, switching stress analysis, efficiency analysis, and comparison with other converters. These are the references. Thank you.